Okay, guys, welcome. This is our last module, Module 9, and this also represents an important but critical branching point for us. This entire course has been about the fundamentals, the beginning, introductory electronic theory and components. But I also recognize that many of you are taking this course because this is a prerequisite for the computing technologies courses. This module right here, specifically this lecture, as we're talking about logic gates, is where we make that tangible connection between the world of electronics and those components and how this actually crosses the threshold into digital technologies and computing. And I hope by the end of this lecture, this illuminates not only the past 16 weeks for us, but also is indicative of the fundamentals of what computing is built on and based on. So without further ado, last module, module 9, we're going to kick it off starting now. All right. If you'll remember from our last lecture, we talked about transistors. And I'd like you to recall transistors are semiconductor conducting devices used to amplify or switch electronic signals and electrical powers, right? We're using them to control voltages and also potentially magnify or amplify voltages. We're building off of that now that we know the physical component, the theory behind it, and we're going to actually start talking about the role of transistors in digital logic. And you'll also understand what digital logic is by the time we finish this lecture. So, as I maintain, transistors are the most important factor in computing, period. We could not have modern computing without transistors, and now we'll know exactly why. In this lecture, we're going to talk about the predecessor to the transistors again, but in terms of computing, which I hope makes a little more sense to you. We're going to evaluate how off and on equates to decision making. We'll talk about voltage being a determinant in Boolean algebra. We'll also understand what Boolean algebra is by the end of this lecture. And we will have a brief touch on binary and binary calculation, something that you've probably seen already, something you most certainly will get into in more depth as you get into the computer networking, specifically CCNA 1. And we're going to touch on it just very quickly so you can see how that translates between voltages and binary. We'll talk about logic gates, obviously, some theory, and then the practical usage and the setup of logical gates in your projects and schematics. And we will talk about the future of calculations in the computing world. So let's kick it off. So, counting mechanisms is what this all comes down to. If I were to surmise the entirety of computing, it's essentially counting and representation. And we've come a long way in the terms of counting and representation, from the first being nomadic herders who were keeping track of their livestock without a formal number system by just placing rocks in a pile to represent each individual of whatever their herd of choice was, to the dramatic increase in calculating technology, which is the abacus, to switching and gear systems, the ENIAC computer, which we talked about last lecture, and also the Colossus 2, another code breaking system, to modern computers. So these counting mechanisms have evolved, as has the technology behind them. Essentially, we're looking at physical manipulation to electromechanical to the digital systems that we know now. And everything from there on will be branches from these first foundations. And if we were to look at those as a continuum, that continuum of representation, you can kind of see how we've progressed. And also how those mechanisms have increased. You also note that they have some overlap. Physical manipulation of a rock or an abacus is also inherently tied to manually or physically moving a gear, or the electromechanical mechanisms. Electromechanical mechanisms such as relays start to overlap when we start to talk to digital systems and the actual physical movement of a reed switch to make current flow. And then as we get into more dynamic dynamic switching methods. I want you to keep in mind that we have a very robust history in the continuum of representation from the beginning to current, and I'm sure it's only going to get richer as we go on with the next technologies. So I'm going to say this again, and I'm going to continue to say this. It is absolutely key and critical to recognize that the ability to turn the flow of electricity on and off is the anchor to what we're talking about. So much that I'll say it again. The ability to turn the flow of electricity on and off is as a key anchor to what we're talking about. And that basically props up the four horsemen of transistors, right? What we can do with this stuff. We can represent a numbering technology. We can perform mathematical calculations, believe it or not. We can set ourselves up for an understanding and a usage of Boolean logic. And from there, we can do decision making. All of this flows from this key principle of our ability to turn the flow of electricity on and off. Pretty much the entirety of this course was us on the precipice to get to this point, to understand this concept. I hope that you recognize that that's extremely important. If not, I'm sure you will in the next couple minutes. So let's start with numbering systems. How do we represent our numbers with electricity? Technically, we're not representing our number system. We're abstracting it with another number system that we can. And that number system is binary, literally meaning of two states or two states. And the relationship between electricity and binary representation in computers or in circuitry is key. Instead of a base 10 number system, we have a base 10 number system because theoretically most of us have 10 digits on our hands, on our two hands. It's easy to start to count and think in terms of this. We're using the binary system, which only has zeros and ones. Essentially what we're talking about is the concept of electricity either being present or absent. 0 meaning no voltage, or 1 being voltage represented. We can see here in a pseudo representation of a voltmeter that there is imaginary threshold, right? If the voltage does not cross the imaginary threshold, if it's lower than that threshold, that would be considered a 0. If it's above that threshold, we can assume that it is a 1. So the presence the presence of voltage would be considered on, and we can represent that with a 1, and the absence of said voltage would be considered off, a switch either being in the on state or off state, a binary state switch either being off or on. And we also call this a logical high or low respectively. And you'll start to recognize why we call it a logical high or low. And if you look at the visual representation, it's pretty simple to see why we call it a high or a low. 1 being high, 0 being low. All right, so a question that's often asked, and I ask this a lot myself, we're limiting our number system to just two states, a 0 and 1. Couldn't we do more with a more robust alphabet, if you will? And the answer is, of course, we definitely could. We could have such higher fidelity of numbers and resolution of representation of numbers if we had more numbers to choose from. We could probably do much more complex mathematics and much quicker with more numbers. But there's some inherent problems when you consider adding more numbers to the alphabet, to the roster, if you will. And I'll try to explain those to give you demonstrative proof on why the binary system works for us. So here we have visualized another, let's say, oscilloscope screen showing a continuum between 5 volts being the highest and negative 5 volts being lowest. We'll just assume 0 volts is the very middle, that red line in the center. If we have too many intermediate states, right, more than just a high or low, you see here I am trying to represent a base 10 number system being 0, 1, 2, all the way up through 10, if we were to try to identify that a voltage at this level were a 2, there's not much room for error and there's not much room for anomaly. Unfortunately, though we have a very good mastery of electronics and electricity, voltage, and current, we have so within a range of specifications. It's not perfect. And as we talked about before, if we start to introduce electricity and the movement of electrons and magnetism, which are so intrinsically tied, we get more of this anomalous behavior and it becomes less concrete and harder to keep a discernible voltage, especially when you're looking at nuanced and fine resolutions. Okay, so the more intermediate states we have, if we instead of doing just a 1 and low being a 0, if we try to add, 8 more different states, there's less room for error and the anomaly that moving current presents. Also, interference, like I was saying, is present when we're talking about electricity and magnetism. The two play off of each other. And polarized outputs, I mean maximum extremes like high at the top and low at the bottom, work better. Additionally, voltage does not rise or fall instantly. We've spent a lot of time looking at wonderfully produced square waves, but when we have different components within our electrical circuitry, we don't see these straight 90-degree jumps that go up and then fall offs. Typically, what we do is we have um, like orbiting electricity, we have other components or capacitors and other electrical fields that delay the drop or the rise. We were talking about ramping up and ramping down. That's very frequent, especially when you're talking about higher voltages. That ramp up is not as steep and the ramp down is commiserate with that. So we like to think that the world is a instantaneous 5 volts we're jumping up and then we'll be able to drop down. But it's not like that, especially when you're using things like contact switches. There's things called electrical bounce. So we just don't have the perfect world of these square waves all the time. And then lastly, when you have these intermediate spaces instead of definitive zones where something can be a logical high or a logical low, we get into this place where we need to have more impeccable timing. And a lot of the circuitry that you see, especially in projects that require multiple components together, there's timing involved. Everything works on a clock cycle. That's why we use these crystal timers to make sure everything is marching to the same beat. With more intermediate states, we need to have a greater mastery of the timing, the beat to which our electrical projects or applications operate to. So I want to also point out it's not that bad to only have a binary state. I mean, as you can tell, looking at current technology, with our phones, the computer that you're viewing this on, and everything else behind it, we're doing pretty well with just two states of being essentially, right? Either off or on. I'd also like to point out that every living thing using our DNA is coded with only a 4-character alphabet, and that's the entirety of the living planet that we know. So, half of that, not too bad. We're doing okay. All right, so some more rationale for binary, and also stemming from the ability to turn the flow of electricity on or off is absolutely key. We can start getting into mathematics, actually doing calculations with just a 0 or a 1. And it's not dissimilar to the way we do it with a 10-base system, right? We have a 0, and then we go all the way up through 9. And in base 10, once we've surpassed 9, then it just kind of rolls over like an odometer. And then the tens place gets a 1. And then we go back to 0 in the ones place. Well, similarly, binary does the exact same thing. The only difference is a 2-number roster. So as you can see here, a 0 is obviously a 0. A 1 is a 1. But if you were to go above that, because we only have zeros and ones to work from, we just move over. And instead of the tens place, it's the twos place. So the second from the right place is actually representative of a 2. If you were to do one more than that, it would look like 11 if you're talking in base 10, but we have a 1, 2, and 1, 1, which equals 3. So here I've drawn this out a little better for you. I'm here looking at 4 bits of binary and reading from right to left, ones, twos, fours place, and an 8 place. And you can see each successive number we go is basically like saying to the nth power, right? 2 to the 0 power is 1, 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8. So I hope that makes sense to you. You're going to see a lot more binary and a lot more representation of binary as you move in through your educational career in computer technologies. And then you're also going to move on to hexadecimal, which is a whole nother beast. But we're fine with just binary for right now. And of course, any number system that you can count in, you can also perform calculations in. Really quickly, I just want to point out, because in this example, there's a 1 in the 8th place and a 1 in the ones place. 1, 0, 0, 1 in binary equals 9, right? There's 1, 8, and there's 1, 1. 8 plus 1 is equal to 9. Okay. So, as I said, we can count, so we can add. So an example, like we were just saying, if you have a 1 in the ones place and you add another 1, you only have 0 and 1 to work with, you carry that forward. So 1 plus 1 equals 2. This is the 2 representation of binary. We can do the same thing with a larger number, and it works in exactly the same way. And this is why binary is so great in digital logic, because it's pretty self-explanatory when you can visualize it. Right here we have a 1, and we have a 1 here in the twos place, which represents a 2. So a 2 and a 1 is 3, and that's added to an 8 here, right? Because there's a 1 in the eighths place. So 3 plus 8, 11. If you were just to carry these down, and you can do the exact same thing where we're counting in powers, right? A 1 plus a 2 plus an 8 equals 11. So, we're not going to spend too much time on binary. I should hope that you're at least recognize that when you see binary, that it's essentially, instead of a base 10 number system, it's a 2 number system, and that you can perform calculations, you can perform additions, and you can count just as you could in any other number system. It also makes it extremely intuitive and lends itself well for computers to be able to count, because computers don't use a 10-base system. They use a 2-base system, a binary system, a series of offs or ons, if you will. So that leads us to our next rationale for binary being important, and it's Boolean logic. Binary was quickly adopted for a few reasons. One of them was the intuitive and intrinsic tie between something either being off or on and being able to represent that with electricity, but also we needed to be able to perform logical operations beyond simple mathematics on this number system, this representation system that soon to be computers were going to be based on. And this already existed before the concept of computers had ever been thought of, at least to the degree that we know them of. And that was by an English mathematician, George Boole. So Boole, for which Boolean logic is created a system of proofs and logic, reducing huge statements or very complex statements into a simple set of symbols. And you're going to see how simplified it is in just a moment, but it's extremely core to the idea of being able to not only to count, but to test against criteria, to compare one another. And that's a huge part of what computing is. Not only counting and performing calculations, which is what computers can do far better than our human brains can, but also this ability to create comparisons against sets of specifications. So let's go to traditional algebra, where we think of algebra as having, like x plus y. We're using numbers as the values for variables, or shall I say, we use variables to replace numbers that either we don't know of or we're trying to solve for. And those operations that we're doing are performed mathematically, right? So that's general standardized algebra. So Boolean algebra is a bit different. Instead, all the variables, the x, y, z, throw that out the window. There are only two variables that we're concerned with. It's the concept of something either being true or false. And all of the operations are logical. That means we can do comparisons. We can compare them against one another to see within this whole spectrum of scenarios if something is either true or false. And I hope you're starting to see now how absolutely imperative and important this was for computers, was that there was a comparison, a logical operational language that already existed, that only used or resulted in two states, right? True, false, on, off, 0, 1. And as far as those operations, right, like the myriad of algebraic mathematical operations, were reduced down to only three fundamental Boolean operators, and those are and, not, and or. Just three. So the entire spectrum of variables that could be represented in traditional algebra are shrunk down to just true or false. And then all of the mathematical operations that are represented in algebra are brought down to just three different fundamental operations in Boolean logic: and, not, or. Let's jump into it, and then we'll see how Boolean logic allows us to make decisions, to do decision-making branches, which is essentially the crux of all computers. Okay, I'm going to remind you, I'm going to say it one more time. The ability to turn the flow of electricity on or off is key in these decision-making operations. And these three operations, as we simplified, and, not, and or, are as such. So let's work on and you're going to understand what I mean about Boolean algebraic operations, right? This is the concept of having two inputs. And because we know that these variables, because we're talking about Boolean logic, can essentially only be one of two things. It can either be yes or no, 0 or 1. But in this case, talking about logic, we're talking about true or false, right? So there can only be one of two cases that are coming in to the operation, into this equation. And in this case, for an and, we're comparing two sets of inputs. The input could either be true or false on one side, and then the other input could either be true or false. And the operation, it's the mechanism, it's that black box that everything goes into. Based on the operation, that's what gets popped out on the other side. That's what gets pushed out. So let's say the input coming in is true. An AND operation essentially means that everything must be true in order for the output to be true. Whatever's going into this black box, this operation, everything has to be true in order for the output to represent true. So if input is true, for input 1 is true, and input 2 is true, then the output, of course, is true. Everything has been satisfied. But if only one of those inputs is false, it negates the entirety and is inclusive. It says everything must be true. And let me try to give you an example. Let's say we're doing an AND operation on me. My name is Pizza. Excuse me, my name is Pizza. Been a long day, guys. My name is Justin. True. I like pizza. True. Only I like pizza on Wednesdays. That is not true. I like pizza all the damn time. So the operation, this truth operation, would find that overall the statement is false. Even though I said 2/3 of what I said were true, it requires 100% accuracy in order to output true. Am I telling the truth with those three statements? No. My name is Justin. Yes. I do like pizza. Very true. Only on Wednesdays. That is absolutely false. I will eat pizza in a box. I will eat pizza with a fox. I will eat pizza any day of the week. So, therefore, by the standard of the AND operation, my statements logically are false. Not is a little bit simpler. Essentially, it's just an inverter. Anything that comes in, it's going to be the exact opposite that comes out. Really simple truth table. I say true, outputs false. I say false, outputs true. Really simple. And it sounds ironic, but they're logical with the operation names, right? And is everything, it's inclusive. Not is like Borat, not, right? No matter what comes in, it's going to be the exact opposite. And our final fundamental operation is the OR. OR is a little unique. It can take one or more inputs, and if any truth is in one of those inputs, then it will spit out a true. It's more, it's less exclusive than and. So, an example, if input 1 is true and input 2 is false, the output would still be true. So, put an example there for me. I like pizza. Very true. And it's Wednesday. Currently at this time, it is not Wednesday, but doesn't matter. The day of the week, I don't care. I like pizza, period. So the output is true. And those are the three fundamental operations that I want you to know for Boolean logic. And everything must be true. Not, no matter what you say, I'm going to do the exact opposite. And or, if there's any shred of truth in the scenario, I will take it. It will output a true. Okay. So, we have come and passed up the entire four horsemen for why the manipulation of electricity is key to computing. Let's put it together. All right? We can control electricity, voltage, with transistors, and we can do it quickly, we can do it cheaply, we can do it reliably, and we can do it in much smaller packages compared to the predecessor, the vacuum tube. We have binary, right? We have this counting system. It's got two states that can represent numbers. It can perform calculations, and it melds well with this idea of something either being on or off, voltage being present or absent. All right. Now we have a logical language in which to do comparisons, to do evaluations. This is key, right? So we have got the means to do it, we've got the language to do it, and we've got a way to compare scenarios. And we can, that this Boolean algebra, this Boolean language just happens to work with two states, right? True or false. It's got three simple fundamental operations. There's some more that we could talk about, but the fundamentals are and, not, and or. And we can perform decision making with these. There's just one last piece, and you have the foundational fundamentals of all computing. We are at the mountaintop. I'm going to show you the way. We're right here, guys. And the fundamental building blocks for digital logic in the modern age is on the next slide. I'm building it up, aren't I? I'm building it up. Okay, here we go. Boom. The final piece is that physical device transistors are the operations and the voltages are the variables. You guys were there the entire time, but now we're putting words to it. We know that when we have a transistor, right? By using a small amount of voltage at the base, it allows voltage to flow through the collector and come out the emitter, right? We talked about that last lecture. You guys had it down pat. Let's put it in terms of logic. Let's say a transistor has two inputs and one output. The collector being one input, the base being another input, and the output being the emitter. Okay? We reframe this and we said the voltage input is high going into the collector, and we have a voltage low on the base. No voltage will flow. That means the output will be low, right? We add a 1 on one side, we add a 0 on the other, then we get a 0 coming out. But if we add a 1 or a voltage high on the base, and we have a voltage high on the collector, it lets current flow. Then we have a voltage high. It sounds really, really familiar. Let's talk about this again. Input A, input B, and an output. Let's take a look at a logic table and see how that looks. Input A, voltage high. Input B, voltage high. Output is voltage high. We just talked about that. Let's change it up a little bit. We're talking about one transistor. Let's say I have an input high coming in here, but nothing going into the base. There's going to be nothing that's coming on the output, right? That's a voltage low. Do the exact opposite. We have no voltage coming in from the collector. The base has a voltage, but it's not allowing anything to go through, so our output is going to be low, nothing coming out. And then if there's no voltage going in any side, then the output will have no voltage coming out. If we were to put that into an Excel table, we see this, right? High plus high equals high. High plus low equals low. Low plus high equals low, and low plus low equals low. All right. Everything that we're saying about this transistor is exactly identical to one of Boole's fundamental AND operations, and we call it an AND gate. We have a physical device that uses electricity that we can control to make a decision. We can make a decision. We can have an inanimate object make decisions based on logical scenarios that we line up. All we need to do is arrange these components in a specific way. It's going to be a time delay mental bomb on that one. Let's let that simmer, and we're going to talk about it a little more. All right. So the traditional transistor is never going to be seen by itself as an AND gate in the wild. It's actually two transistors together in series. And this is essentially the way it works. There's a voltage line that comes into one side, the collector of a transistor, and then we can control what that base sees. And then we put another transistor in series. The output, or the emitter of the first transistor, actually feeds into the collector of the second transistor. We can also control the voltage on this base. Now, based on our ability to control the input of A and the input of B and provide power to the entire system, we can create an AND gate. This is the first of three fundamental operators in this entire logical system. We also know that we can provide, by using these gates, we can create mathematics, we can create decision making, we can create addition, we can do any logical operation on a much smaller scale, but scale it up as big as we need to solve complex problems. I'm going to take a moment to appreciate this because I know I'm geeking out on this and I want you guys to as well. Everything that's been that has some digital presence in your life, whether it be a phone, a gaming system, movies, streaming on Netflix, your new televisions, like anything that you have is essentially the ability to control electricity so that a series of ones and zeros can get pushed out of one pipe and processed by something within this series of gates, producing ones and zeros, controlling electricity current itself, and then arranging these logical gates in a way to accept these ones and zeros, make decisions, draw images, make music, stream internet, um, you know, create these fantastic worlds based on our ability to manipulate a gate, essentially the allowance of electricity or the absence of electricity. This is the core. This is like the denouement. Like everything in electronics to date has been coming to reach this fantastic precipice, and now we have the technology that we can because we can do this quickly, cheaply, and we have such finite control. And it starts with just these three gates, not, and, or an OR gate. Okay. That being said, if you were to look at a schematic, it's highly unlikely that you will see two transistor gates in series anytime you see an AND gate. And you will see billions of AND gates if you were to look at any of the devices that you frequent. Instead, we represent these gates with this symbol. All of the components are abstracted away, and you see a conventional AND gate, which kind of looks like a big D, and two lines going into it, two or more lines going into it, and then the output. And you know that if all lines are true or voltage high, then the output is true or voltage high. Let's break away really quick. I want to show you something in the simulator. I bring to you a representation, right? This is a representation of an AND gate. What you see here are two logical inputs, and this is a logical output. I don't have control over the logical output except for with the input. I want to show you that if I turn this high, nothing happens. But you can see this green line represents that I have a logical high, essentially a 1 or a true going into one side of the gate. If I hit the other side, I have now created two truths going into an AND gate. And of course, we have a logical high or a true coming out. So now that we've abstracted away the representation of the transistors, let's bring it back really quickly. So we have our voltage being presented here, and we have an input going into the base. And you can see how the emitter from the first transistor feeds into the collector from the second. If I were to put a logical high, sure, voltage passes through the first transistor, but it stops right here. There's nothing coming out on this output right here. But if I turn this other input, this other base high, controlling this transistor as we talked about that we can, you can see that now I'm able to get a logical high or a voltage high. Or in the language of computers, I would be getting a 1 out, right? I've added two voltage highs and I'm getting a 1 out. That is an AND gate for you. So I hope that made sense. We know how transistors operate, but by arranging them in a specific way, which is again why I said transistors were so key. But their specific arrangement um, allows us to perform logic, and this particular arrangement we call an AND gate. So let's talk about our next gate, the OR gate. The OR gate is a little more confusing, a little more nuanced, but it's the exact same components. It's the arrangement of these components in a particular way that allows the logic to slightly fluctuate into the way an OR gate performs. Now, if you recall, an OR gate, any truth represents an output of truth. So any high logic will give an output of high logic. Let's walk through the simulator and take a look at this. So here is our OR gate. I have our gate representation. Just to prove to you that this is indeed an OR gate, let's walk through the gate representation first. Feasibly, any voltage high or any logical high going in should produce a logical high on the output. Let's test that theory. All right, there we go. So I have one high, one low, high is the output. I have one low, one high, high is the output. Two highs, high is the output. Two lows, the output is low. So let's take a look at exactly how this works. The arrangement is a little unique. I don't want you to think that this wire is actually connected to the one going into the base for the first transistor. We actually have our voltage high going into the first collector. It's not touching this wire. It's completely independent, and it's going into this second collector. We have two inputs going into the base on transistor 1 and then again on transistor 2. Now the output of, or the emitters, the output, is coming and actually connecting. It's being drawn down to ground with this resistor, but also it's attached to our output, which is now showing a logic of low because both of our inputs are indeed low. If we were to change one of these to logic high, what happens is this turns on the base, allowing the current to flow down through the first transistor, out the emitter. It's getting drawn down this resistor into ground, but it's essentially putting a voltage on this line right here. Let's turn this off. If I were to turn this one high, you can see the exact same thing is happening. It's essentially a mirror of the first wire that's coming from the VCC, the current. It's coming down, it's going into the collector. Input is the base, and then it's producing a voltage or current coming out of the emitter. It's being drawn down this resistor to ground, but also putting a current or voltage on the line, producing a voltage high or a logical high. Both of them do the exact same thing at the exact same rate, and if I were to turn them both off, then there is no current that's being passed through either transistor, therefore there is a logical low on the line. Now our last fundamental gate, the NOT. We can also call NOT an inverter because that's really what it does. It inverts the truth table. It takes any logic coming in and produces the opposite. This one is unique. It looks a lot like a traditional transistor setup with one key difference right here. We have our ground trying to draw the current through the resistor out of the emitter, but our output line is actually connected above the transistor itself. We've got a resistor here to pull the current down from VCC, from positive voltage, and then this right here, our input, is attached to the base. Now I want to show you this in action. It's really ingenious and unique because essentially by allowing the base to be energized, it's circumventing the output. So having the high here pulls the current down so that it doesn't go through the output and it forces it through the transistor instead. And that's how we invert our logic. If a line is high, energizing the base, then the current's getting drawn through the resistor, through the transistor, but not through the output, and therefore it inverts the logic. Also, you should note that the symbol for a logic NOT looks like a triangle, but also you'll see that's got this little nipple here, this little bubble. It should be implied that anytime you see this bubble on the output of a logical operator, it's inverting whatever would normally come out of that. So you'll see this triangle, essentially it's telling you that this is a NOT gate, but if you see this on an AND gate, you're knowing that it's basically saying not AND. If it's on an OR gate, not OR. So I wanted to point that out to you. Let's take a look at the simulator, we'll walk through it, and I'll show you how it works in real time. Alright guys, so here in the simulator you can see our gate representation of the NOT. It's currently high, even though there's a voltage low going in, or a logical low. If I turn the logical high on, then it outputs a low. And to give a demonstration of how this works, even though you'll only see the schematic representations, these symbol representations in schematics, um, here's our VCC, our voltage coming in. There's the resistor drawing down the current, and if the base is not energized, then the voltage will go through the line towards the output. But if we turn the base input on, energizing the base, then it will, of course, pull the voltage down to ground, and then making the output a logical low, or a zero. So key distinctive difference there is that the output line is being above the transistor, and that the current is being drawn either towards the ground, away from the output. So guys, that is it for logic gates. I hope that helps kind of illuminate the power of not only exactly what these components do, but also demonstrate that we could not even feasibly have technology near what we have without the ability to make logic-based decisions, and also obviously calculations. And it also demonstrates a huge power within the binary system for us to be able to do everything that we can with essentially a voltage, or the absence of a voltage. So that's that. If you have any questions, of course, please reach out to me. You're going to see that a lot of the content that was in the slide, especially the highlighted stuff, hint, hint, nudge, nudge, is going to be what's in the final. Please recognize and understand the fundamentals of the logic gates that we just looked at, the and, the not, and the or. I want you to work through them at least mentally, and recognize that the truth tables and how they intertwine with the fundamental operations. And that's it. All right. I'll see you guys on Wednesday. Thank you so much.